Good morning everyone. I am Tanushri Dalai from Civil Engineering branch. So in the last class we started your chapter 4 and today we will discuss from the relationship between actual length and effective length, which is already given in table number 11 in IS code 800/2007. So I told you in the last class about these three types of condition, which is known as your end conditions of the column section. According to this, you have to take the effective length value, which is this one and this one and this one, and rest of the conditions are given as here. Okay. So basically, according to the steel design procedure, in case of IS 2007-800, we need only these three types of conditions. Okay. So basically, we use these three kinds of end condition for the design purpose. So now, for the buckling class, so first of all, whenever in the question you are given by a compression section like I section or channel section, whatever that may be, so there are some conditions by which you can identify that the section having what kind of buckling class. So see, here it is the table number 10, which is given in the IS code book. So here you can see, as an example, we take this I section. Okay, and for this I section, there are some limitations which is known as your conditions to find out the buckling class. So the first condition is your H by B should be greater than 1.2. If it is satisfied, then the buckling about the axis of this I section will be in YY axis. Hence, the buckling class will be A. As like that, the second condition is if the TF value, that is the thickness of the flange, if it is less than equal to 40 mm, then your buckling is about ZZ axis in the compression member of I section, and it is undergoes the buckling class of B. So according to these conditions, we can find out the buckling class of the section, and the buckling is which axis we can find out. So here you can see this part. You can see here, this is a channel section, this is angle section, here it is a T section, here it is rectangular section, circular section. So for this kind of section in compression zone or compression member, there is no kind of conditions are there. Directly we can put the buckling class, which is C. So these sections are undergoes the buckling class C. So now comes to the method 2. So in case of method 2, first of all, as your method 1, you have to first of all write down the data givens of the questions. After that, you have to write the properties of the section which is given in the question. Then you have to find out the slenderness ratio and also identify the buckling class of the section from the table 10. So up to this much, the method 1 and method 2 is same. Then from the step 3, which is finding out the buckling class from the table number 10, then comes to the next step, which is step 4. As per the buckling class, we can directly put the value of FCD, which we can find out from the table number 9. So in the table number 9, it is categorized into 4 types, which is A, B, C, D, and each of the section indicates the buckling class A, B, C, D. So for buckling class A, we can find out the FCD value as per the slenderness ratio from the table number 9A. Similarly, for the buckling class B, we can find out the FCD value from table number 9B. As like that, we can find out the FCD value for the buckling class C and D from the table number 9C and D. After that, we know that the compressive strength, that is PD, which equal to FCD into AE. So we can directly put the value of FCD from the table number 9, and the cross-sectional area, which is AE, we know that as per the section, we can find out the AE value from the steel table. So now we will discuss a numerical based on compression member. So see the question. Calculate factored axial load on the column ISHB 400 at the rate 806.38 Newton per meter. The height of the column is 3 meter and it is pin-ended. Use steel of Fe410 grade. So what are the data given here? The section is given, which is ISHB 400 at the rate 806.38 Newton per meter. The height of the column is given as 3 meter and it is pin-ended, and the grade of the steel is Fe410. So here the actual length is given, which is 3 meter, that is the height of the column. So we can easily find out the effective length of the column. So now comes to the table number 11 from the steel code. So here for the pin-ended at the both side of the compression member, which is column, so for the pin-ended, the condition is effectively held in position at both the ends but not restrained against rotation. So this one is your condition applied for the calculation of effective length. So for this condition, the value of effective length will be 1.0 L, that is 1 into actual length of the column. So now we can find out the effective length of the column by the help of this formula, which is 1 into L. Then we have to assume the Fy value that we know. For Fe410, the Fy value is 250 megapascal, and gamma m0 we know 1.10 from the table number 5. Then Young's modulus, that is E, which is equal to 2 into 10 to the power 5 megapascal. After that, we know the section of the column, which is ISHB 400 at the rate 806.38 Newton per meter. So ISHB means it is a I section. So here the section type is given, which is 400. So now we can find out from this section the properties of the specified I section from the table or from the steel table. So in the steel table, we found out the H value equal to 400 mm, then BF, which is width of the flange, which is equal to 250 mm, then TF, which is thickness of the flange, which is equal to 12.7 mm. After that, TW, which is thickness of the wave, which is equal to 10.6 mm, and the cross-sectional area of ISHB 400 is equal to 10466 mm square. Then here the radius of gyration is provided in both the axes, that is in ZZ axis and YY axis. So in the ZZ axis, the radius of gyration is equal to 166.1 mm and the radius of gyration in YY axis is equal to 51.6 mm. So first of all, we need to find out the class of the buckling. So for that, we need to put the formula H by B from the table number 10 in IS code 800-2007. So now we put the formula here. So H by BF, that is the total depth of the I section divided by width of the flange. So we know that the value of H is equal to 400 and width of the flange is equal to 250. So which is 1.6. So 1.6 is greater than 1.2. So here your condition is satisfied. That means your buckling is occur in the axis of ZZ. So for that, your buckling class is A. Then the second condition is TF should be less than equal to 40 mm. So the value of TF is equal to 12.7, which is nearly or less than equal to 40 mm. So the second condition is also satisfied. Hence, the buckling is also about in YY axis. So for the YY axis buckling, the buckling class is B. So here we know that this I section is having a buckling class along the ZZ axis as well as along the YY axis. So now we can find out the compressive strength value along the ZZ axis and along the YY axis. So now we can find out the FCD value, which is compressive stress value, which is equal to Fy divided by gamma m0 whole divided by phi plus phi square divided by lambda square to the power half. So to solve this formula, we need to calculate the phi value and lambda value. So for that, first of all, we know the lambda value, which is equal to Fy by Fcc whole root over. So we know that your FCC value is equal to pi square E divided by KL by R to the power